Hi guys, welcome. This is a session focusing on a lot of concepts around generative AI, aspects about GANs, aspects about prompt engineering, how agentic AI basics works. So in this session, I will also try to give it like a story. A girl called Sophie, who's an art student. We use that as an analogy. We also try to understand the concepts around generative AI. Sophie joins this art class. Teacher starts giving her instructions. This is how you paint or draw a cat, and shows hundreds and thousands of samples. This is how a dog is painted, and this is how a landscape looks. Right? So starts taking it. It's very similar to how we train AI ML models, and her brain absorbs all these and slowly start extracting features, making connections and the meanings. Does the patterns are recognized? Every cat that she sees, she starts realizing that okay, cats do have pointy ears compared to a dog which has an elongated muzzle-like face which extends forwards. And then when you look at landscape, scenic views generally have a horizon, the sky, the mountains, trees somewhere in the background. So this helps Sophie or even an AI or an ML to understand patterns between data that is being shown. The more and more data you give, the more and more it becomes better and clearer with the patterns that it identifies. But let us also quickly review a bit of supervised learning because it's very important. The way supervised learning works is it takes inputs, which is thousands or millions of images with labels, where clearly a picture is shown and said this is a cat, this is a dog. Based on this guidance or the supervised learning, the model gets trained and starts recognizing patterns between so many of the images. Now Sophie also is learning about different images and how it looks and starts making a list of features between these objects. For example, now she knows the cats have pointy ears, they have whiskers, they have claws, and based on that she is able to draw boundaries. Whenever she sees a picture of a dog, she'll put it on the right because it has wagging tails, wet noses, elongated faces. Whenever she sees landscapes, she's going to put them on another side, groups them. So she's now becoming discriminative, as in is able to categorize and say, okay, this is not a cat, this is a dog, this is not a landscape, this is a cat. You show an image to a neural network and ask what it is. First thing is it starts taking in, looks at the picture, the pixels, the patterns, the images, and then starts understanding, okay, I see scenery, nature, sunset happening across it behind a temple, right? So all this is nothing but classification and also recognition. So we were talking about Sophie, who from being an art student has become a great recognizer. She's not going to now say it's a cat. She's going to say that this is a cat sitting on a lawn with a scenery in the background. She can describe an image very clearly, right? This is how even a AI using supervised learning starts beginning to recognize and describe objects, right? So supervised learning, as we know, we have used it in email spam, on recommendation systems like Amazon. User bought a guitar, they also bought the picks for the guitar or a guitar bag, right? Person A bought an item X, then they also bought item Y, right? So then there's face recognition, which we talked about, MTCNN and other things. So why are we talking about supervised learning? Today it's about generative AI, but it is very important to understand the foundation of generative AI, which is all about how do you define objects and recognize things and how do you see patterns. These learnings will be used for generating whatever that has been learned in supervised learning. Now that she has mastered recognition, the next challenge is about how can she start painting, how can she start generating, creating new masterpieces, original pieces, artistic work. So Sophie is going to start imagining and organizing ideas in her mind, right? And that is what's going to make us understand how generative AI works and how you give a prompt to a tool, it starts generating what you want, right? So how does this actually, the imagination for humans work, right? So when somebody gives a prompt that generate a cat which is sitting in a field or generate a cat that is drinking milk, first thing is we're talking about a cat. The whole image of a cat is not stored or remembered by Sophie as it is, right? Sophie or the AI model understands the essence of a cat or what are the concepts or features of a cat. Let's call it catness, for example, right? It has fur, it has whiskers, It has playful eyes, like we know cats are into. So all these are already there somewhere in Sophie's mind, or the AI knows these are many of the features of a cat. Then we said cat drinking milk. So we also understand the concept of a milk bowl of milk, and the drinking action where the tongue is come out and all that. So the imagination starts giving us a shape, and that gives ideas in the head, and then the strokes start beginning and the AI starts generating too. And this is actually, think of this as a theme park. Has so many different areas, right? There's a play area, there's swimming pool, water world, there are these giant wheels and all that stuff. So similarly, in our whole AI or generative AI, we as humans, we have in our brain so many areas for different things. Same, the AI has different zones or a map of thoughts. What are the features of a cat? It is kept in some place. What are the features of a dog? Let's call it a dog zone, a cat zone. Now, if you also think of a car zone where there are cars, and if I ask you a question, right, where would you place a cat and a dog and a car in the map based on their similarity, right? So the cat is a pet, dog is a pet. Cats generally are with humans in houses eating food. They may have a small dog house or a cat house, right? What about a car? Car, the moment you imagine, you start thinking cars and trucks and Formula One racing, driving on the highways, and also different colors and styles. So if you think of this mental map or a theme park of all these things, cats and dogs are somewhat nearer, whereas a car is slightly far away, right? So this becomes an idea, and this also is an idea called similarity search that we'll be using later to do that. Now, this whole mental map that I just talked about, it's also called, or the term used is latent space. So latent space is the mind of the AI, where instead of storing millions of photos and pictures of cats and dogs and cars and many other things, it only stores a compressed data of the features. Like, what is a cat, right? The cat has eyes and whiskers, how humans think. It will have its own geometric mathematical way of storing different features of a object that it is shown, right? So again, here each of these concepts will be represented by points on the map or the network, and the distance between 2 points also shows how similar or how far away they are. This is also called cosine similarity or similarity distance. And then all the patterns start coming together to identify the whole thing as an object. So latent space, by the way, is one of the very important concepts in generative AI. Whether you're using GANs, DC-GAN, many other places, latent space is extremely important. To understand what is latent space, just think of it as that mental map we made of a theme park, where we are keeping different things and having the similarity search. The latent space is also somewhat similar. For now, we can keep it like that, right? So again, now in this map that I talked about, or the latent space, right? Let's say there is a royalty area, which is all about castles and kings and queens and stuff. There is also this smiley land or smiley island or smiling land, where there are a lot of faces which are all showing smiles and happiness and laughing and all that stuff. If these are all different zones in your map, imagine somebody asking you to show some royalty or show a smiling face. You're mixing a man face with a smile, so it becomes a smiling man. You're taking a dog and adding a royalty robe or a scepter in hand, and suddenly ideas from a dog zone and a castle zone are combined. And the way it works is, iterations is, it starts becoming smoother and smoother. Yeah. So if we are doing this, how does it store and what does it store? If I have 200 pictures of a dog, which dog will it store, or as a reference, or which dog's features will it store, or will it store individual pieces of the dog in different formats and all? So one of the things the latent space does also is, it lowers the dimensions. Like, lots of bells and whistles or lots of information is chopped out, and the core idea of the object or of the item that we need to store is only stored, right? So because of that, the biggest advantage is, let's say I train a model with 500 photographs of a human male, right, of a man. Now, instead of storing all 500 pictures, it will finally store only one picture, not even picture, actually numbers, vectors, and in that it will store only an average of all these 500 people humans. So the next time we ask a prompt to generate a man's face, it will take that average face and starts adding some noise around it or some more features around it, makes it better, and generates a new picture. So this is how it becomes very effective, and this will also means that you're not storing millions of pictures, thousands of pictures, or very high resolution, high quality pictures, but a lower dimensional picture which is only used as a reference. If you want to imagine this, think of the directions from your house to your hometown, for example, right? Or like to your house, to your grandma's house or a friend's house. Would you want to print out pictures of the whole map and carry it, or would you just need the GPS coordinates and use Google Maps, right? So the Google Maps is already there. You're only getting the GPS coordinates from the API, and that is very small. It's only numbers, a set of numbers that is being passed continuously, so your maps work very well. So that's a great example to remember for lower dimensions. Instead of storing the whole map direction turn by turn, you actually just store the GPS information and draw it on a given map. Now, how does this actually use this concept of the map, right? So it only stores the pointy ears, the playful eyes, the whiskers, those kind of words. They probably even get converted to numbers, and only probabilistic data distribution is stored in the latent space, which means I'm not actually storing one exact cat, or I'm not storing multiple cats, but I'm storing a distribution of numbers or embeddings which gets converted back to a cat, and every time it will not take exact number but takes a number from a distribution. This is a little more statistics. We don't want to worry about it right now, but the idea is it takes the core information stored in the latent space or the map and starts adding a lot of features based on its training, and then it generates the cat. In our mental map, we said there's a cat zone, there's a dog zone, there's a royalty zone, like that. So she's now in her mind going towards a cat zone and starts imagining all the things that she remembers about a cat, and starts drawing a totally new cat which is not there. So now, how does your Sora or ChatGPT or Quen or any of these Gemini, all these tools generate images for a given prompt? Now we are not talking about just a cat or a dog. We are talking about, say, a monkey wearing a Hawaiian shirt, sitting on a beach, sipping a cola or a Heineken or a coffee with a laptop. That's your prompt, right? How does it actually generate such a good clarity, highly optimized image, exactly like the way you asked, right? So this is where, back to the latent space, the map, the mental map that we talked about, the cat zone. Let's say there's a dragon zone, there's a cat zone, or there's a beach zone, right? It takes a cat, all the features, starts painting or drawing a cat. It takes all the features of a beach, starts adding that beach also along with the cat, starts taking a Hawaiian shirt and starts bringing that in, and over iterations it will see that the shirt is now on the cat, and it has so many pictures, images of different people and other funny pics where people are holding glasses, coffee, beers, whatever, and tries to bring that in. And again, like I said, it will not always pick the exact item or the numbers from the vector embeddings, but it picks it from a distribution, which means when you say a coffee mug, it may pick a coffee mug which is white in color with no print, or it may pick up a coffee mug which has some print on it, or it may totally pick a different kind of a glass cup, right? Now here we are talking about a cat and a dragon zone. Combine those, the hybrid creation, you're getting a cat dragon, right? So that is how your blending of ideas work, and you end up getting beautiful pictures getting created by all these tools like Sora, ChatGPT, Quen, and many more things, right? So where do we use all these generative AI aspects, right? So we have text to image, right? The same thing we talked about. I said cat with a crown. It will say crown means royal, cat means cat. So it maybe generates a image of a cat holding a scepter, wearing a robe, and having a crown, sitting on a throne maybe, right? Every time you ask, it will generate another image, but it is always going to be a cat in a crown. Now, There's another thing that I'm sure you all have been using in your Snapchats or Instas or any other tools that you use. You take your picture where you're in a shorts and a t-shirt and say, uh, convert this image to me wearing a suit, right? Or you ask that you're standing on a beach, take a picture, say, change my background and make it a skyscrapers or New York City, right? Or take an image and say, make it a Van Gogh style. And it is called style transfer. The actual person or the object is not changed, but only the styles are changed. So there is a concept called style GAN. Style GAN is used for style transfer. You can also use many other techniques. And I'm sure you've played around with a lot of tools, changing your face to Tom Cruise's face, or making your face younger, or how do I look after 20 years, or a serious photo of yours, you want to convert that to smiling photo. Nowadays, big fashion is bringing back people from the dead, right? Like we've lost our grandparents or somebody. Take the pictures, use some tools, and suddenly you got your grandpa speaking and saying, hey, study well or be happy or whatever you want them to say, right? So what we talked about is latent space. It's a very important aspect. In fact, latent space is what makes the concept of generativeness or the creativeness, because I take an item like a car, I remove the body, all the plastic and everything, only the engine, the wheels and the chassis is remaining, and then I give it to another person, say, hey, build a car on top of it. Now this person is going to build a completely different looking car. Maybe it's a different color, different shape. Maybe he converted a Maruti Suzuki to an Audi, right? So this is where the imagination map or the mental map comes into picture, and this is what makes it creative. I hope you guys are catching this. Also, it's endless creativity. Keep giving the same prompt again and again and again, and you will always see a new image getting generated, and it looks slightly different. Pick the best one that you like, and this is what we are talking about as dreaming. This is AI dreaming, and that's what is generative AI, right? Now, while latent space is a great concept, it's like an engine of a car, we also want to understand all the other components that makes the car run, right? So there is this important aspect called GANs, right? If you're learning generative AI, you're not just learning LangChain and RAG and you're fine tuning, but you're also learning GANs, right? And GANs is very fundamental. 6 years, 8 years back, I started studying GAN, and it's like wow. And what it was then to what it is now, even crazy now, right? It's there's so much of improvement. C GAN, DC GAN, style GAN, cycle GAN. So many GANs have come. Super GAN. You're improving the resolution and all that stuff, right? So let's come back to Sophie, who is an art student who can recognize things very well, and now she's saying, hey, I want to build the art, right? Okay, I understand the mental map, the latent space, the imagination map. Let me start doing the work, right? And she starts painting. What happens with the painting? The first painting, she thinks it's good, but she doesn't know if it's good, right? She needs somebody to tell her whether it's good or bad, or if she needs to improve, or how good it is or how bad it is, and is she totally off the mark, right? So that's where a critic or an adversary or an enemy or a nemesis comes into the picture, right? So this makes the whole generative AI very interesting, right? So there are two roles in a GAN. Generative adversarial networks has two components. One is a generator, another one is a discriminator. That's the components. If we look at it as roles, Sophie here in our example, she is the creator or the generator, right? She is creating or generating new paintings one after the other, and she doesn't know how good or bad it is, right? And now the judge is like the discriminator, who is going to look at every time a painting is given. He looks through it and says, no, this is not good, or I don't like it, right? So the generator and discriminators are same in AI, where they are components that the generator keeps generating, discriminator keeps rejecting it, and that's how the contest begins, right? So let's say Sophie wants to paint a Van Gogh style of an image or a painting, right? Now the discriminator or the judge is super strict. So she makes a painting, he says, oh, this is too fake, right? This is like 40% good, right? I don't like it. All the brush strokes, the things, it all looks like you've used a stencil or a copy paste or whatever. I don't like it. So now Sophie, the rejection is actually a lesson, right? She's not going to get disheartened saying, oh God, she's going to say, I'm going to learn from my mistakes. And that's what your generator discriminator in GAN does. So what is this generator discriminator actually doing? This is the concept of an adversarial game, right? So to understand this game, or the adversarial game, let's look at a chess game, or the chess as a game where there is a student, chess player, and there's a teacher who's a chess master. The student is learning from the master and playing with against him every time he's losing the game, right? But every time the student loses the game, the teacher or the chess master is going to say what mistakes he's doing. He's saying, hey, your openings are not good. Please work on the openings. Do better openings, right? Learn Sicilian defense. Learn your Roy Lopez. Learn English opening. And then the student starts learning and improving, but again loses. Now the teacher is saying, well, there's problem with your middle game, right? So you have to improve on your middle game too. The tactics and puzzles, work on that. The student learns, and then the next games again he'll play better but still loses. The judge may say, or the master will say, your end games are pathetic. You're playing so well in the beginning, you know are taking pawns and pieces, positionally playing well, but in the end you're making silly mistakes because of which you're losing the game. So the student is learning again and again. Finally student becomes so good that he's giving a tough fight to the master. It's going to make the master also start getting a little better and starts becoming expert in spotting the mistakes. Like his beginning opening is good, middle game is good, end game is good, but somewhere in between he's not doing some things like checks, captures, attacks, right? So he's able to find those flaws and tell him, and this whole adversarial relationship will make the student better. In our case, the generator will become much better and improved, and it starts generating better and better samples. So coming back to Sophie is painting an image. The judge is critiquing and telling, no, this is not good. He's giving a score. Sophie is learning. Okay, last time I got a score of 3 out of 10. Now I got a 5 out of 10. So I did better. Next time she gets 7.8. Then she gets 9. There is going to be a time when the judge is not able to find that easy mistakes. He's going to look through, through the magnifying glass even better and find a very small, tiny hairline mistake and becomes even more stricter. And this cycle makes the generation better and better. And as I mentioned, there's the technical components or generators, discriminators, and this whole adversarial trainings. This is what makes it a GAN, right? So just to repeat, generator, you can think of it like, I want to create a picture of a car, right? What does the generator do, right? The generator could be a simple program which draws one rectangle and two circles and say, this is the car, right? Discriminator is pissed off. Discriminator says, no, this is not a car. These are just a rectangle and couple of circles, right? I need to see the windshield. I need to see the tires, the rubber, the doors, the handles, so many more things. That's a loss function, right? The loss function is sent back to the generator. The generator says, okay, fine, I need to do all this, and makes a better picture. And discriminator again does the discrimination, saying, okay, this is not correct. Again, still you are missing out. The paint is not proper. It needs to be 3D. It looks better. So this whole adversarial training is what makes the GAN's technical components achieve what we want. And finally, we achieve victory because the discriminator is no more able to differentiate between the generator, the real ones or the fake ones, right? Is this really a Van Gogh painting? I don't know. It could be. All elements are there. Everything is perfect, right? The chess master is no more able to beat his student because he's learned everything perfectly with the feedback cycle, right? So Sophie is creating beautiful paintings, and you're not able to make out whether it's Da Vinci's paintings or her own paintings, right? She has become that good. So there are a lot of applications generating. You cannot imagine how good the images are coming out these days, right? I mean, I'm sure you would have seen. You can ask for a prompt like a boy and a girl or a man and a woman are walking on Mars with the sun and the earth setting in the background, and make it realistic. And it'll be so realistic, it'll be shocking that it's a painting or an image or an actual photograph, right? Celebrities' faces, deepfakes. Again, deepfakes has a very negative connotation. It has a lot of good things too, but it has a bad things because people are taking advantage of this. So there's ethical AI that needs to be implemented. But deepfakes are good. Imagine recording a lot of materials and training people without having to speak. I'm speaking right now and telling so much. I can also just write this small script, generate it in ChatGPT, give it to my avatar, and it will create a deepfake of me. Right? Can be educational. Style transfer, as we talked about. So now that we looked at the latent layer in a generative AI, we also looked at GANs, generative adversarial networks. There's a very important concepts in generative AI. This is pretty cool. This is very interesting, and this is probably new to many of you guys, the diffusion models, and some of you might have even used it, implemented it, and worked on it too. So let's see this guy called Alex. He's a sculptor, and then he's become a digital sculptor too now. So he used to chisel, and now chisel marble and make sculptures. Now he's actually using third-party tools and image and video tools and creating digital sculptures, right? Creating 3D models and all that stuff. So how does he do it, and how does the digital images and videos are created, right? So that's a concept called diffusion model, right? So what is it, right? So let's wait a second to understand the concept. But before that, diffusion model is used by so many tools. If you go to any of your Sora, Quen, ChatGPT, which I'm talking about, when you ask for generating an image specifically, it would use diffusion models, right? There is a tool, DALI, framework, Stable Diffusion, Midjourney. I'm sure you've heard of many of these. They all use diffusion models, right? And it takes a prompt, it converts that into an actual image by reading the prompt and understanding it. And this is not like just GAN where it takes an average photo of an image and adds stuff to it, but it's very different. It's a lot of mathematics, it's a lot of neural networks all working together, and it almost sounds like magic, but it's math, right? It's mathematics, not mathemagic. So how does this work, right? So now Alex wants to make a sculpture of a cat from a real block of stone, for example, right? Or if he's doing it digitally, we call that noise. Initially, all we have is noise in diffusion models. We don't know, just a set of random numbers or text or whatever it is. And we start chiseling away all the bad parts to finally make the cat that we want. The prompt here is a cat sitting in a field, right? So basically a sitting cat and a little bit of background around it. Sitting cat is what we want to create a sculpture or an image out of this. And as I said, the marble block is nothing but the noise in the diffusion models. So yeah, let's go further to understand this very exciting and very important concept to understand image generation, right? So first of all, technically, what are the components? In GANs, we had generator and discriminator. Here, we have a forward process and a reverse process. That's the technical concepts for generation of new items, right? So what is the forward process? What is the reverse process? So even before that, I want you to imagine something here. I'm not showing the image here, but imagine this. If you're holding a perfume spray, right? Like it could be a Calvin Klein or Dolce Gabbana, any of those perfumes, or I take any, I don't care. Press the perfume spray, and suddenly there's a lot of one single small drop becomes hundreds and thousands of micro drops. I hope you're imagining this. If you have watched any movies in a theater in 4DX, the mist and all coming, right? This is all diffusion process. A single droplet is now broken down into hundreds and thousands of droplets, right? So that's diffusion. What we do is, if you already have the chaos or the diffused items, if you bring it back to the drop, that is the reversal of the process. And this is kind of very similar or exactly what happens in diffusion models. For example, take a photograph of a person, take a scissor, start cutting it in 4 pieces, 8 pieces, 12 pieces. You know how you're getting to actual same image to a lots of pieces which are meaningless, right? That's the forward process. Now you record the whole thing and join them back from last step to first step. That is the reversal process. if you keep doing this and training an AI model, take something, break it or destroy it or spoil it, and then hope you have recorded it and then reconstruct the whole process back. This is diffusion models, or the process of diffusion. It's funny the way it sounds, but actually it's a lot of mathematics and neural networks, and it works very well, right? So let's look at the forward process. What happens? Let's say we already have an existing sculpture or a model of a cat, right? It's a beautiful cat sculpture. It's a perfect statue. The first step we have to do in forward process is add damage, destroy it, or like start destroying it, start killing it, right? So how do you do that? Like you can throw stuff on it like mud, or start taking some knife or blade or something stronger, chisel, and make cracks. Take a hammer, start beating it, and start creating cracks and dents and scratches and everything else. Stupid, right? I mean, it sounds so funny, like what the hell is going on? We are thinking destructive, right? Continue doing this, step by step ruin is what we are saying this. So keep breaking this down further until the statue becomes totally unrecognizable, right? So you cannot even make out this was a cat. So many pieces have fallen down, you have no idea what's what. This is chaos, right? This is high entropy. So many steps, finally we have nothing but lots of pieces of the material, right? And this is the forward process of diffusion models. This is what actually the AI model does from the input data. It destroys it in a specific manner, right? So the question is, like I said, you're thinking, what the hell is going on here? Why are we destroying things? What is this whole destruction, right? So if we understand how a perfectly beautiful sculpture or a photo or an image gets broken down into totally unrecognizable noise and chaos, then if you reverse the process, you're reconstructing to what it is. So tomorrow, instead of completely deconstructed or spoiled or broken thing, I just give a lot of clay, right, or a lot of mud or some material. You use the same process and reconstruct it back. And while reconstructing, you do not, let's say, remember exactly every small piece and speck and dust. You'll still end up somehow generating very close to what it is, right? So this is what is the concept of a diffusion process. And like I said, in the reversal process, you start taking the noise or the chaos or the block of clay or whatever, and start taking the bigger chunks first, making the shape, then start refining the details, add touches and polishes. Suddenly you have a beautiful cat. This is the reversal process. So the forward process, the reverse process. That's how the training is done. The train model is now very ready. Just throw a lot of dust or noise or whatever towards it. It will reconstruct the way it should, right? Now, the beauty about this is, again, endless creativity, infinite possibilities, right? Because you don't know what's the starting point. You take a lump of clay, start shaping it, and start adding more and more shape to it. It finally becomes something. You can take a look at this image here. There is a cat in the middle. So we said a cat sitting in a field or something, right? That's what got generated. The one behind it, same prompt. It's looking slightly different. It's not turned to the right, it's looking straight. The one on the right top or the left top here, actually the hand is up in the air. Crazy, right? A lot of creative stuff. This other cat, it has its eyes open, while rest of the cats has their eyes closed. So this is what is endless creativity or infinite possibilities I'm talking about, that the diffusion models keeps generating more and more and more of those images that we want. Yeah? So now that we understand the latent space, the GANs, the diffusion models, let's quickly take a look at what these LLMs are, right? Everybody knows LLMs now. I don't even have to tell you what is LLM, large language models. But how does it work internally? A little bit knowledge is important. That's how you understand generative AI, right? So we had Sophie, we had Alex. Now there's this other guy called Sam. He's not an artist. He's not a sculptor. He's a reader, right? He just reads lots and lots of books, and he starts taking so much of info in. Typically, how a large language model also keeps taking in information and starts becoming smarter and smarter, right? So think of Sam like this ultimate librarian, right? He has read millions of books, looked through lots of websites, articles, novels, scientific papers. So now his brain is like super brain. And the best thing about him is he has perfect memory. He doesn't forget, right? He knows everything, every word, every pattern, every connection. It's all in his mind, right? So very similar to that is an LLM. You give a lot of corpus data, it reads and reads and reads and stores and stores and stores. Ultimately it becomes a large AI model for language. That's LLM. And it's not just about reading and remembering or storing. There's one more crazy thing about SAM or the LLMs. It can discover relationships, right? When you say king, when you say queen, it says, hey, there is a relationship. Both are royalties, right? Both have power. Both are leadership, right? If you say doctor and a patient, it says, okay, now we are talking something common here. Patients meets the doctor, doctor treats the patients, diseases involved, medicines are involved, right? So hot, cold, warm, yeah, it's related. If you say Paris, it's related to France. All this, the LLMs or the SAMs, they are able to relate that. If you go back to the latent space, we were talking about the mental maps, similarity search, cosine similarity, that's what is happening here. So the closer things are grouped together, and that becomes a very interesting aspect of your LLMs. LLM has one more important thing. It is not just search. It's not like SQL Server, MySQL, where you say select star from get the data. No, right? It trains in a very interesting way, fill in the blanks, right? Predict the next word. What's the next word in the story? Once upon a dash, it fills immediately time, because that's how it has been learning so many of the books and novels and articles and everywhere. It knows that the probability of a word after once upon a is 92%, right? So once upon a, almost 92% of the times it's going to be time. Very rarely it's a different word, right? Very interesting. So this, what comes next, predicting, makes our LLMs very smart and starts generating. So when you ask for a prompt, like I want to write an essay about Europe, for example, or medieval times, or culture, or religion, right? So how does it do, right? First of all, it analyzes the context. It looks at what is the question, what are you asking for, what have you written to me, what's the question you're asking me. It gets a full understanding, and then it starts coming up with prediction of words. It goes one word at a time. It looks at thousands of possibilities, and then it starts ranking them, gives a ranking and says, okay, this should be the first word. Then it chooses the next word. What's the next best word after I choose this word? It keeps repeating the process. It so happens so fast. You ask a question, you see pages worth of text is generated, because these are all trained on GPUs and hosted on very powerful machines, and very well trained, high accuracy, high precision. And it's like a storyteller. It's like I ask one of you, like, tell me a story about a dog and a cat, or tell me a story about a sparrow and a crow, right? You will start telling that so quickly, because your brain has learned it since you've been a kid. Your mom, dad, grandparents might have been telling different stories about a king or about something else, and you don't remember any of those words in sequence, but you're able to very easily start making up, generating, creating all these words, and start making these things, right? So how does it actually work? Very simple. It uses an architecture called transformer. Not as simple, but simple to understand. Transformers are neural networks, a special type of neural networks, two neural networks, encoding, decoding, like encoders and decoders. But the beauty of transformers is something called as attention, right? You go to a movie, watch the movie, like Demon Slayer or whichever movie you saw recently. You come back and Tom Cruise F1, one of the movies, right? Mission Impossible. And then you come back and you explain it to your friend, what's the movie story. You'll say it in a very short one para, two paragraphs. What is it that you paid attention to? That's what you're going to tell, right? Your brain stored only the important items. Rest of it you're generating or you're creating. That's what transformer does too, right? The neural networks uses attention, gives weightages. I'll tell you one example. There is a sentence: I went to this self-service restaurant, or let's say I went to this bakery and I ordered a couple of vegetarian puffs. I ordered the buns and toast and some cakes. I ate them, and then I walked back home, and I'm now inside my room, right? Do you think all these words are stored in the latent space or this neural networks. No, it removes a lot of unnecessary words. It adds stemming and many other things. It gives weightage or attention to the words which are very important, and then it tries to give the attention or the weightages and then uses them, right? So this is transformer architecture. Context awareness is very important. You ask question number 1, it gives you an answer. Then you say reduce the number of words, or like what was my Uber expense for the month of January in Bangalore, for example. And the next question I'm not going to repeat for March, right? I'll just say what about March. It is aware of the previous context and it will still answer or respond to me, right? So this is context awareness. And large language models, massive scale, billions of parameters. Again, what are these parameters, right? Have you heard of these LLMs which have 70 billion parameters, 7 billion parameters, 1 billion parameters? Very simple. These are nothing but the weights and biases in your neural networks. If I have lots of neurons, those small circles in the neural network, if you have seen the image, all the weights between neurons and all the biases in those neurons are nothing but the parameters. So if I say a model is 1 billion parameters, that means there are 1000 weights and 1000 biases. That's it, right? It's very simple. So it's 70 billions, 8 billion, Mistral 7B, Mistral 8B, Mistral 70B, DeepSeek. All these have so many parameters that are weights and biases that are stored. So it has that much of information. Right? But then there is a problem with these LLMs, right? It's not like LLM is not like your answer, right? Okay, I have this medical problem. I'll not go to a doctor. Let me save some money. I'll ask ChatGPT. That's a bad idea, right? Because the LLMs do not know everything that humans do, right? They do not have any personal opinions. It just states stuff and it will just tell what it has learned factually, and there's a limitation of cutoff. Whatever it has learned until a certain date, it does not have latest information. There is no memory between two different conversations, for example. And the biggest problem is it can tell you very confidently incorrect answer, right? Very confidently say this is what it is and it's wrong. It will be wrong, but it will say with so much of confidence that you'll believe, oh wow, this is correct, this is what I should do, right? So be very careful that don't rely on ChatGPT for everything or LLMs for everything, but they're very good at pattern matching. Use it as a tool, still use your brain, right? So that's important. It is limited by its cutoff date and its training data, right? So there are many use cases of LLMs. I don't even have to say it. Language translation, creative writing, summarizing content, and all this, right? So now that we talk about LLMs and prompts, there is also the concept of prompt engineering, right? Everybody knows prompt engineering now. I can even go through this really quick. So instead of just saying a small English sentence, if you give more information, you get better outcome, right? So that's what is art of the prompting or prompt engineering. Let's come back to Sophie now, right? So Sophie is a painter. She's an artist, right? If you say paint a fast animal, right? I don't know what she's going to paint, right? Because I did not give her enough context. She can paint a picture of a cheetah which is running in full sprint. Maybe that's what I wanted. Or a falcon, a very fast bird that's diving down. Or she might even paint a speed racing car. For some reason, she thinks there's an animal driving that car, right? He drives like an animal, right? So it's a lot of approximations, right? You did not get what exactly you wanted because your prompt was not good, right? So prompts do matter. If you guys have watched this movie called Bedazzled, I really want you guys to watch that to understand prompt engineering better, or like bad prompts. Every time this guy keeps asking Liz Hurley, like this is what I want. She's a genie. He rubs the genie and she comes up and he asks for something. She gives him everything, but literally, and things go really bad for him. If you watch this movie, you know what I'm talking. Otherwise, you can watch it sometime. So it's like Sophie is also like a genie, right? You say this is what I want you to paint. That's what she's going to paint. You don't give enough information, she's not going to do that. So you know the definition, so I don't have to get into it. Crafting precise instructions, right? So it's like a instruction manual, and it uses that, takes every detail that you've given in the prompt and builds it. So let's take a look at the fast animal example, right? That was a weak prompt. It's very vague. There's so much you can interpret it, right? Instead, look at the good prompt on the right side. A majestic cheetah mid-sprint on the African savanna at golden hour dynamic motion, wildlife photography, National Geographic style. It's very specific, it's detailed, and it's actionable, right? So the more good or strong your prompt is, the better your results are going to be, right? So that's what is the whole prompting all about. And we have zero shot prompting, few shot prompting, multi-shot prompting and all, right? So what does that mean? I'm sure you probably know this already. To quickly talk about it, if I say paint a cat in a spacesuit, the painting may come like anything. It's not very specific, right? Like there is a spacesuit, a man lying on a wooden floor inside the house with a spacesuit. Stupid, right? I mean, why would you be wearing a spacesuit inside the house? And there is a cat. It's not inside, but it's on him near the helmet. So maybe the cat did want to go inside, but the helmet is closed, right? Whatever. The idea is, this is not a very good prompt, and it's very generic, very vague. If you give the right prompt, the expectation is something like this, right? If you give a really good prompt, you would have gotten an image something like this, but you got this. So this is, sometimes zero shot prompting has its problems. So then how do you improve a prompt? You can use something like few shot prompting also, right? What is few shot prompting? It's not like asking multiple times also, but it's also about giving more examples. Take a look at this, right? I'm saying classify this review I got from a movie or my restaurant, or a new piece of text, to whether it's a positive review or a negative review, right? I have a restaurant and I have a lot of reviews on my restaurant. I want AI to look through it and say, hey, you got like 45 positive reviews and 2000 negative reviews, right? I want it to tell me how good or bad my whole restaurant is. So by just giving that prompt, that would be vague, but or like a prompt, I would give a few shots, like few examples. Look at the first example I'm telling the prompt, right? The new update is great, it fixed all the bugs of an app, right? So I'm telling also the answer, sentiment is positive here. My order arrived late and damaged. The sentiment here is negative. I'm teaching the prompt or the LLM that, hey, this is what I'm expecting. Give me sentiment negative, sentiment positive. So with this, the prompt is very clear and detailed and instructional. It gives you a very good outcome. So what does it mean? Your iteration is also key. You tell Sophie to do something, she makes something, you give a feedback, iteration happens, then next time she starts understanding, okay, this is what you're asking. So in your chat GPTs, if you go for one of your previous prompts, you'll see you asked something, it gave something, then you refined, saying no, I wanted it in paragraphs, not as bullet points, or I wanted in bullet points. It will give that, right? So it's a learning iteration. So now we know prompt engineering, RAG, GANs, latent space and all. There is also something very interesting where everything is coming together, right? Earlier ChatGPT used to give us only text, but is it the same now? No, there's so much more. Now all the people like Sophie and Sam and Alex are all coming together, and we get something better. It's called the universal artist, or the other word is multimodal. So we have Sophie, who's the artist, and then we have Sam, who's the librarian, and Sam understands language, right? English, is very good at it. He remembers every words, everything, like the LLM, the language. And Sophie is a good painter and artist. If they both work together, all I have to say is, I want a monkey on a beach wearing Hawaiian shirt with waves in the back. Sam is going to interpret that, make it much better prompt, and then tell Sophie that, hey, start with the brush stroke, do this, do that, and then Sophie will give the exact painting that you want. Okay? So let's see an example. For example, a cat wearing a beret reading a philosophy book in Parisian cafe, right? So that's pretty crazy prompt, right? So how does Sam and Sophie work on this? What do they do, right? So Sam understands every single word. He says, okay, beret means cap, right? And it's Paris, and so many things are there. And Sophie here is the master painter. She is going to understand first before start drawing the brush strokes and everything, and both of them will start doing the imagination and creation and brings that to that. So how does that actually work, right? So we asked for a cat in a beret in a Parisian cafe, right? So first of all, Sam says, okay, it's a cat, right? What are the features of a cat? Characteristics, behaviors. He's going to explain that to Sophie, right? And then beret means it's a French cap or a headwear. So he explains how does it look, what it is. Then philosophy book, So make it more intellectual, right? It's a intelligent cat reading philosophy, and it's Parisian cafe. So try to bring a Eiffel Tower or something in the back, right? So now Sophie starts the drawing. She starts creating a cat. It's very blurry initially, and she takes a canvas, random noise, pixels, starts creating something. There's a book that's supposed to come. She's trying to draw outline of a book, and then she starts giving it a little more features. It's grainy, but it slowly started shaping up, and then starts putting some colors and starts getting better, and then gives more touch-ups and glows and everything. Now you've got a beautiful picture of a cat wearing a beret in a Parisian cafe holding a philosophy book, right? So that's very beautiful. It generated exactly what you asked, and that's what happens in a multimodal models, right? So multimodal training means you're also giving it images and texts and pairs. You give an image and say this is what the image is described. Alternatively, you give the text first and then generate an image and show for this text this is the image I want. And they also have a shared latent space now. Remember the latent space we talked about in the beginning, the mental map. So whatever you're creating as a cat, whatever you're creating as a cafe, now there is a common latent space, which is why the whole thing becomes a single picture and not three pictures, one a cat, one cafe, and not Paris, but it's all a single picture, right? So that's what is the beauty of the technology here, right? So technically what all happens, text becomes image, image gets text, there's audio integration, video generation. Once upon a time it was just a dream. Now it's a reality. So many beautiful tools. They generate videos, audios, and many more things, right? So where is it all used, the multimodal, right? I don't even have to say. You want to write a book, a movie, or you want to create entertainment, education, notes, chapters, lessons for students, design, even for visually impaired people. We are doing AI smart glasses there. So many places we are using multimodal models, right? So it's like a universal artist which can do a lot more than just text or just one image, but it can bring text and image and audio, video, everything together, and that's what it is, right? So now there is the concept of RAG. I want to tell you guys that there's already a RAG video that we have made. You all have tried it, many of you, and you have generated the outcome, and I've seen many of you do that. So I'll not go deeper into this, but the idea is this whole librarian Sam, who had a lot of knowledge, has one problem: frozen in time, right? Sam has read a lot of books and then stopped taking in any more information. So Sam does not know yesterday's breaking news. Sam does not know sales report of the recent quarter or your private files in the company. Now, how do we fix this problem, right? There are two approaches. One is RAG, one is fine-tuning. RAG is easy. We have talked about it. You dump all those files or the PDFs or the data into a folder, write a RAG, retrieval augmented generation program using LangChain and your sentence transformers, vector embedding, similarity search, and get the outcome. And we know most of it. I hope you have seen my other videos, so I'll skip through this. It converts the documents into embeddings, stores similarity, semantic similarity, and does the search, and we get perfect answers. Say, what were the key points from the Q3 sales report? It does not go to the LLM, but it goes to the newly updated data and matches it and uses the LLM's power to give beautiful English and understand. So general knowledge and library pages and perfect answer is an analogy you can think of, right? So there is the research knowledge comes up with a final quality article. For example, a journalist wanted to do an article and publish it. So we know this. I'll skip through this. So now we talked about another method that's called fine-tuning. Fine-tuning probably is very popular these days. If you have a AI/ML interview, if you have a data scientist interview, I'm sure they are already started asking you what is fine-tuning. Have you worked on fine-tuning? Have you done just a POC or actually implemented a production-ready fine-tuning? Do you know PEFT? Do you know LoRa? Do you know QLoRa? These are all the questions I'm sure some of you might have heard, and it's very important to understand fine-tuning, right? So what is this fine-tuning all about, right? So we know Sophie, right? She's a art lover. She wanted to be an artist. She understood the recognition and patterns. Then she started creating. She used the advanced techniques. She had a coach, the adversary, the coach, the tutor, and she started getting very creative. But the problem with that is Sophie is just an artist and not a doctor, right? Or Sophie is a very good artist, but she's not a financial expert, for example, right? So if you start asking her to start drawing a painting of some surgical tool that she is not aware of, she might conceptually do something. But what if we train Sophie to learn everything about anatomy and surgical instruments and diagrams and medical concepts and everything? Now she can become a specialized medical painter, right? Or a medical sketcher or a diagrammer. So that's what's the concept of fine tuning, where you take an LLM, which is very generic, and then you train that LLM to learn about financial domain or learn about your healthcare domain. Suddenly this LLM, which only knew good English, good concepts, generic Wikipedia stuff, is now talking like a doctor, talking like your doctor, your hospital's medical practices. It has learned everything and it has become a specialist, right? So how do we do this, right? See, if you take a bucket of water and throw it to the ocean, right? The ocean is not going to become unsalty or sweet or anything, right? Because the amount of changes you made was very less. So similarly, if you try to fine tune a big model, just changing some extra information, it's not going to work out. You have to do something very efficient, right? You have to do something very smart. That's where the PEFT comes into picture, right? PEFT is parameter efficient fine tuning. What does that mean, right? So if you remember your model, say, just for the sake of example, let's say it's 1 billion parameters. What does that mean? 1000 into 1000 weights into 1000 biases, for example, makes it 1 billion parameters. Now I will use only a subset of the parameters and train that with the new data and attach it to the main model. And now I've increased the efficiency by adding more parameters which are specific to certain things. And this is where one of the PEFT methods called LoRa comes into picture. So I have 1000 into 1000 or M into N, like a 7 billion model or 70 billion model. What I do, I take that M into N, introduce a small r. For example, we call it as a rank. So I'll do M into R plus R into N. This practically becomes M into N, right? Now this R, I'll take it very small, right? It's a low rank. I'll take the rank of the number R very low. Like I'll take it as 10, right? So now 1000 into 10 is 10,000 and 10 into 1000 is 10,000 again. So I only have 10,000 plus 10,000, 20,000 parameters to train. And I will add this as an adapter. If you understand a little bit of software development design patterns, there's an adapter pattern. I attach this to the model so that at the entry, when a question is asked, it will check, do I already know this in my newly trained fine-tuned knowledge? Then it tries to answer that and uses the rest of the LLM knowledge. So you're actually tuning existing LLM using PEFT LoRa method and making it more intelligent and more precise for medical data, for example, or financial data or healthcare data or some other data, right? If you quantize this model using 16-bit, 8-bit, 4-bit, whatever, you now get QLoRa. And I hope this helps you in your interviews. This is a frequently asked question in your AI/ML interviews, generative AI interviews. They ask you, do you know fine tuning? Do you know PEFT? What is LoRa? What is QLoRa? I hope this information will be very helpful for you to answer that question. You can do more reading, but this is kind of a concept to understand. Yeah? So it is efficient, it is cost effective. If I had to retrain my whole 7 billion model, I would be spending $500,000 to $1 billion, right? Here, it's very cost effective. I'll hardly spend $10,000, $20,000, maybe the GPUs or the whatever else, right? And it also preserves the original skills. It's not like I'm changing, but I'm fine tuning. I'm only improving places where it has to be affected. So that's PEFT. And there is a process to it that you use a pre-trained model, then you bring in your specialized data set, that's your healthcare records or medical records or financial data or your stock market trading techniques, intraday momentum trading techniques or something, and add it to an existing LLM like Mistral or ChatGPT or Gemini, and fine tune it, right? Then it becomes a specialist model. So what's the difference between RAG and fine tuning? Both can achieve pretty much similar stuff. Like, my existing LLM does not know certain things. I throw some documents in a folder. So every time it has to search, every time it has to learn on the spot dynamically and say, so there's going to be a performance issue, it's going to be delayed. But fine tuning means it actually has learned so much about the models and data set that we want, and it has become a specialist. So the efficiency is better, and people are going towards fine tuning nowadays. Yeah? So medical, legal, financial, and many more things. Right? That's fine tuning. And then there is LangChain, LangGraph. We are kind of running out of time, so we can cover this in our next session. But you have already used LangChain, I guess, in some of our previous videos. And there is AI agents and agentic workflows. We will hopefully cover that in the next session. We will talk with a beautiful example of a studio where there are multiple artists, there are workflows, they use a lot of tools, come up with beautiful, and they can scale up. 20 different clients are giving 20, 30, 40 different requests. It is able to handle, it is able to coordinate and all that stuff. So I hope, I know this is a lot of information to take in, but also these are all nice examples, easily relatable, not complex. The example of Sophie and Alex and Sam hopefully has been helpful for you guys. So I just will ask you, if there's any area that you did not understand, ask me in the comments, questions, or go back to the video and look at it. There's a lot to learn here, and I hope this was helpful for you guys. Thank you guys. Thank you so much.